Welcome everyone. Let's jump right into a fascinating explainer today on how cutting-edge AI is literally being squeezed into smartphones to help save our global food supply. We hear a ton about AI writing emails or generating art, right? But today we're looking at something with massive, life-or-death implications. We're going to unpack a technical report detailing a highly accurate image classification model built specifically for crop disease diagnosis. Here's our roadmap for today. We'll kick things off with a global food crisis, jump into the plant disease dataset, see what it takes to make AI edge ready, check out training for accuracy, and finish up with democratizing agronomy. Let's get right into it. Section 1. The global food crisis and the staggering stakes of crop health. It is so easy to just take the food in our grocery stores for granted, but the reality of global agriculture? It's incredibly fragile. To put it in perspective, picture this. By the year 2050, our planet is going to need to feed nearly 9.7 billion people. That requires a massive, totally unprecedented surge in global food production. It's a daunting number on its own, for sure, but it gets kind of terrifying when you consider what we're actually up against right now. Tragically, every single year, even as global demand climbs, we're currently losing between 20 and 40% of our global crop yields to undetected pests and plant diseases. Just think about that for a second. Up to 40% of the food we try to grow is wiped out before it even has a chance to reach a plate. And that translates to a staggering $220 billion annual economic hit. But this isn't just a statistical gap on a spreadsheet. When a harvest fails due to undetected blight, local communities face skyrocketing food prices, families go hungry, and smallholder farmers can lose their entire year's livelihood. The traditional way of diagnosing disease relies on expert agricultural knowledge. That's expensive, it's highly localized, and honestly, it's just way too slow to stop an outbreak from totally decimating a field. Which brings us to Section 2, the plant disease dataset, and how we actually go about building the AI's brain. To solve this crisis, developers needed incredibly high-quality data to train a model capable of instant, on-the-ground diagnosis. You can't just teach an AI about one type of plant. Agriculture is a wildly diverse ecosystem. The absolute foundation of this model's visual recognition is the plant diseases 100K dataset. We're talking about over 100,000 high-resolution images across 14 distinct crop categories. Think apples, corn, strawberries, rice, the whole shebang. And within those specific crops, it covers 67 different health statuses, showing both completely healthy leaves and leaves exhibiting various pathogenic states. This massive scale is exactly what's necessary to train deep neural networks without running into severe overfitting. But having a mountain of data brings its own unique challenges. Because we obviously don't have the exact same number of images for every single plant, developers had to tackle something called class imbalance. If they just left it unchecked, the AI training process would naturally favor the larger classes, just to minimize its error rate. Basically, it would get lazy and just guess the most common crops. So to fix this, developers calculated specific mathematical weights for each crop status. They multiply the average loss of response tokens per sample by this status weight. This ensures the model is forced to learn the rare diseases just as well as the common ones. Moving right along to Section 3, making AI edge-ready through micro-level optimization. Now we're going to zoom into the dense technical weeds. How do you fit a massive AI into a farmer's smartphone without literally melting the device? A solution is completely useless if it requires a massive server farm in the middle of a rural cornfield, right? It has to work on the edge, meaning directly on the user's local everyday device. The developers selected Gemma 4 E2B IT as the base model. This was a brilliant move because it actually features a native vision encoder, and with only 2 billion active parameters, it's inherently optimized for the tight speed and memory constraints of edge devices. So it's fast and small enough for a phone while still packing a punch and maintaining really high accuracy. But let's be real, 2 billion parameters is still a bit heavy for a standard smartphone. To make it truly edge-ready, they had to shrink it down using a technique called quantization. You can think of this like compressing a massive high-resolution photo into a much smaller JPEG file, but applied to the complex mathematical brain of the AI itself. To actually pull this off, the developers used an incredible sequence of mathematical gymnastics. First, they compressed the model's weights by a massive 75% using 4-bit normal float quantization. Next, instead of retraining the entire massive network from scratch, they used parameter-efficient fine-tuning, or LoRa, to adapt just the necessary attention layers, throwing in a 5% dropout for regularization.
Finally, during the actual math operations, they temporarily use B-float16 precision to prevent calculation errors, also known as overflows, while the model is actively learning. And to keep this highly compressed digital brain stable, they utilize some seriously clever memory-saving tricks. For instance, gradient checkpointing recomputes intermediate steps on the fly instead of storing them, which saves massive amounts of VRAM. An 8-bit AtomW optimizer actively prevents those dreaded out-of-memory crashes, while gradient clipping stops wild mathematical swings from ruining the model's weights. And to guide the whole learning process super smoothly, they used cosine annealing. That means starting the learning rate at 0, warming it up, and then curving it slowly down to help the model settle into the absolute best possible mathematical solution.
Section 4. Training for accuracy and proving the concept. Look, all that complex math is only useful if it actually diagnoses a sick plant correctly. So let's check out the results and see how this architecture really performed during its training phases.
Because Gemma is an instruction-tuned model, developers were able to maximize its potential through clever prompting. They literally forced the AI to output its diagnosis in a strictly structured JSON format. The prompt explicitly tells the AI to analyze the image and output its findings strictly as a JSON object with crop and status keys. By forcing the model to identify the broad crop type first, say a strawberry, and then nail down the specific disease status, it navigates those 67 possible outcomes so much more accurately. The training data revealed a really rapid convergence. Now, an epoch is just a full pass over the training data. And after a mere 3 epochs with a batch size of 32, the AI's error rates absolutely plummeted. That steep drop happens both during training and on brand new validation images, showing the model is quickly figuring out the vital visual boundaries between healthy and diseased states. The raw numbers here are incredibly impressive. Over the course of the training steps, the training loss dropped all the way from 0.40 down to a stabilized 0.002. But more importantly, the validation loss, which measures how the AI performs on images it has literally never seen before, hit a highly accurate 0.005. This proves beyond a shadow of a doubt that the model isn't just memorizing the training data. It can actually generalize exceptionally well to brand new, real-world crop images.
Finally, Section 5. Democratizing agronomy and the macro impact. Let's zoom back out and see what these tiny mathematical weights, quantization tricks, and JSON outputs actually mean for humanity on a global scale.
In practice, this is exactly what it looks like. An expert agronomist stuffed right into a smartphone. It instantly and accurately identifies complex diseases like cedar apple rust, apple black rot, and northern leaf blight, directly from a simple photo taken right out in the field.
And that leaves us with a pretty profound thought to end on. We started by looking at a $220 billion problem that's constantly threatening global hunger. But if a hyper-compressed AI, running locally on a cheap device, can instantly empower a smallholder farmer in a remote village to detect blight and save their harvest before it spreads, is this exact intersection of micro-level AI optimization and macro-level agriculture the ultimate technology we need to protect the 9.7 billion people of our future? It is absolutely incredible to see how a few lines of code and some intense mathematics can quite literally help feed the world. Thanks for joining me on this explainer. Keep learning, and I'll catch you next time.